Hi everyone, let's go to lecture 3, inferential statistics. This is something I actually do a lot of, and it's something that if you do any kind of human-computer interaction or visualization work, you hit all the time. If you have to do any kind of reports and make any kind of meaningful observations about your data, it's extremely useful. If you were doing data mining, I'm not sure how, it probably does apply, but I'm not sure how much. But for your reports, if you're going to tell me that there is if you're trying to report something about how effective your system is, you need to have these. So it may not seem critical at first for some of you will, but let's see what we have. So you can't really test everybody. You sort of have to base your conclusions off of a subset of the data. That's the idea of an inferential statistic. That's why you do a random selection of people to do presidential polling, and then you make inferences about the general population based off of what people say. You do the same thing with vaccinations. You give a random subset of the population a vaccination, and you see who gets COVID and who doesn't, if the person with the vaccine gets COVID versus people that get the placebo get COVID. And notice also for vaccinations, in case you're wondering, it's actually double blind. The person who is getting the vaccination or the test doesn't know if they get the placebo or not, and neither does the person giving the vaccine. It's completely randomized. The reason it's completely randomized is because you do not need or do not want to know who is getting what. It turns out that in other cases, like when they were doing early AIDS research for drugs for AIDS, people would, if they didn't know if they were in a control group or not, but the experimenter did. I'm trying to remember how exactly it worked. They were swapping pills so they would get 50% of the time they'd get the proper pill, and the other time 50% of the time they'd get a placebo, and hoping that everybody gets some kind of beneficial effect of it. It screws up the experiment royally, so you can't tell who's getting what. And so having a completely double blind and saying we don't know what you're getting, sort of, it's the same as just mixing up your pills, for at least from the statistical perspective of the user, or the person getting the pills. They don't know what they're in. Their doctor doesn't know. Nobody knows other than the experimenters, and they're not directly talking to you, so therefore you don't know what you have, and you can't really infer anything. And you also shouldn't know who the other patients are either, so that you can't swap pills. So this is directly related to HCI. It's maybe related to machine learning. I would love to hear from you guys if you have cases when you need to know this. But the idea is, if you have a subset of the data, what kind of conclusions can you make? Can you infer about the general population with if you only have a subset? One of my lines is, if you say that there's a significant difference between my system and system X, or the original system, I'm going to laugh in your face if you do not have a normally distributed data set, or if you didn't randomly select, or any number of other things. What we're looking at is, if you don't do your stats right, essentially, any claims you make are incorrect. You're claiming something that's not valid. Your logic is not valid. And so what we need is truly random sampling. And if you're going to use the word significant, by the way, it actually means something very important to people that do this kind of statistics. When we say significant, we normally mean statistically significant, and that means by random chance. Normally, it means by random chance, there's a less than 5% chance that the effect you're seeing is due to random chance. If you've never seen this before, like a lot of my undergrads have never seen that before, that takes a little getting used to. For the people that have been dealing with this for a while, you're going to go like, yeah, of course. Why do you have to tell us this? It's obvious. It's not obvious to people that haven't been dealing with this. So when we say users performed a set of standardized tasks, significantly shorter time using our interface foo compared to some interface bar, what does that mean? It means for 27 degrees of freedom, we have a t-test value of 3.4. We'll talk about that in a second. And here's the kicker, that the statistical chances of this effect being due to just random chance, who I chose for my user group, or the order in which I did the experiments, or anything like that. The chances of this being purely due to random chance is less than 5%. That is our typical bar for what we mean by statistically significant. So if you say the word significant, you better have a p-value backing it up. Don't say significant if you just mean like it looks better. No, if it looks better, say it looks better. I won't believe you. I won't believe your data, but fine. I won't chastise you that much. But if you say it's significantly better, our system is significantly better than the old way, you better have a p-value. Okay. The idea here is if I have the population, the full set, the universe of all possible, if you want to look at it from set theory standpoint, if I have the universe of all possible people or everyone in a population, I'm going to choose a sample of those people, a much smaller group than the actual population size. So the size of the population is way, 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 way bigger than the size of our sample. So it could be, the stakeholders are all gamers in the US, and so you talk to a subset, some group of gamers in the US to evaluate how they're using their system. Some small sample group gets a vaccine versus the entire United States getting a vaccine is not possible for vaccination trials. And then based on the statistics, you can make claims about the population in general because it works for the small sample, and the small sample is really representative of the general population. What are the chances of you just happen to choose the wrong group of people? If you could experiment on everyone, you wouldn't need inferential statistics. You would just get the data. You would say, this vaccine works. It worked on every person in the US. What they're trying to do is, I chose a subset of people to get this vaccine. Let's go back to an earlier, I think I mentioned, I have a video that I had to throw away, but I think I mentioned this in an earlier video. Vaccination in the US it's hard to get a representative sample of users in the US for vaccinations. Certain demographics, certain groups of people are not as trusting or wanting, they don't quite trust the medical system as much as others. One of those classic examples is the black population in the US is famously adverse to taking for medical treatments and medical experiments. They don't tend to participate on as regular of a basis as other members of the U.S. population, and for a good reason, because there's been a long-standing history of some horrible atrocities being done to them in the name of science, not like horror show kind of things, but the Tuskegee syphilis experiment, if I'm pronouncing the town right, I always just read it, was essentially them giving black men syphilis in the 1930s and then watching them and how the disease progressed in these people from 1930s onwards. What's important is they did not tell the participants in this group that they were getting syphilis. They didn't tell their spouses, they didn't tell anyone else, but they injected people with syphilis to see how the disease progressed. They then get antibiotics which deal with syphilis, so they have a cure for this disease that they're studying, and they continue the trials, still not letting these individuals get an antibiotic to deal with their syphilis so that they now eventually know that they have, and they continue to push against and prevent them from getting antibiotic treatments to deal with their syphilis just to keep the trials going. They unilaterally chose black men in Alabama rather than the general population. It was not a representative sample of people. It wasn't for the black community in Alabama. It wasn't for anything else other than to study syphilis for the general population, but they chose a particular subgroup and experimented on them without their knowledge. This is a reason why they had a huge overhaul in the United States about medical ethics and informed consent. And thank goodness for that, but it is... You're not good when you're talking about a vaccine experiment, vaccinations, and when they're testing that for COVID-19, they're having the case of they do not have enough. They don't have enough minorities involved in the vaccination trials. They're actively having to go out of their way to try and make sure they get a representative sample, because what they're going to get if they don't do that is you'll know if the vaccine is effective on, let's say, if you only test the vaccine on middle class white people, you won't know if it works on more economically disadvantaged white people. You won't know if it works on the black population. You won't know if it works on various people of Asian descent. You won't know if it works on recent immigrants. You won't know anything else because you'll just be testing on this one subset of people. You need a representative sample of the entire population. And if you don't have that, you cannot make correct inferences about your data. Turns out that's a problem in psychology. Most of what we know about psychology is based around, how well undergraduates can do a particular task. All our knowledge about perception, all based around undergrads doing this task because they were getting university credit for their psych courses. It's not actually that accurate because we're testing a non-representative sample. Anyways, that's another aside here. So when we're talking about variable validity, just let's go over a couple terms. When we have an independent variable, it means it is the thing that we are manipulating. It might be you're getting a vaccine. It is independent of these other things. I am controlling it. The dependent variable is the thing I'm measuring. It is the thing that depends on the independent variable. So getting COVID is a dependent variable. So it could be I give somebody this treatment and independent variable, they recover, dependent variable. It could be, this is normally for controlled experimentation, but it is something that you would want to look out for. The thing you control is your independent variable. The dependent variable is the thing that you measure. A confounding variable is one where it's another factor that you're not really monitoring, but it's there, and it's sort of baked into your system. So a confounding factor might be for, let me see here. If you're looking at caffeine consumption amongst gamers, I'm trying to think of something weird here. What we can say is they look at non-gamers and gamers, and they conclude that playing video games makes you drink caffeine. Why? Because when they look at gamers versus non-gamers, gamers drink more caffeine than non-gamers. What they're not paying attention to, the confounding variables, what time are gamers awake and when are they playing the games? Because if they're trying to stay awake late at night, then the reason they're drinking caffeine is not the video games, it's the fact they're awake at night. Things like that. It's a confounding factor. It's something else that they didn't take into account, but it actually can be the cause. And then there's also something we're going to call isomorphic factors, or isomorphism. We're going to talk about this maybe a little later if we need it for your experiments, if you're doing experiments. An isomorphic factor is if I give you all of your exams are supposed to be isomorphic. As in, I can take one exam, give it to one class 1 year. I give the next year a different exam, but it's equally challenging, equally hard, covers the same material. It tests the exact same thing. And so no matter which version of the exam you get, they should be equivalent to one another if we have standards year after year. Isomorphism is just meaning it's the same. You can change the form. It doesn't change anything. So what are we trying to do? So a typical case, we might want to check the difference between interface foo and interface bar. For you guys, it might be, I want to see if there's a correlation between, addition of a crosswalk and, that's correlation. Before we had crosswalks and after you have crosswalks. So before you introduce crosswalk into the city of Ottawa, this is the number of accidents you have. After the crosswalks are added, this is the number of accidents you have. Before and after, or this region which has a high, this group is highly taxed, this group is not highly taxed, and or how when we added new taxes, this is the change in the amount of money they spend in the community, something like that. We're going to look, so there's correlational analysis, and then we also have experimentation. I want to just briefly hit those. I think most of you guys are going to be doing things like correlational analysis, as in, I know these two factors are correlated with one another, and once you know that there's a correlation, you can sort of infer if you can generalize that for the population afterwards. A correlation is if this thing changes, the other changes by a set amount, or by they are related to one another. It might not be linear, but there is when I increase the size of the target I'm trying to click, the time at which it takes me to click that target goes down. If the target's further away, the time it takes for me to click the target goes up. If we are doing experimentation, which I don't think you guys quite get, but you might get it, we might have to hit this particular situation. If you're testing people, there are two different things you can, normally we break it down to two different forms. A between subjects design means you give, interface foo to one group, and you give interface bar to another group. You give the vaccine to one group, you give the placebo to another group. That is a between subjects design. You have two different groups, you give them one the experimental condition, the other one the control condition. One, the default, what was done before condition versus the thing you're comparing it against, and the experimental condition, the thing you're trying to test how effective it is. That's a between subjects design. A within subjects design is you give one person both. And you say, how does that work? Well, you can do that for a lot of things, like perception tests, right? Can you see this light under this condition? Can you see this light under these conditions? How well do you drive when you're sleep deprived? So you test how they drive before they're sleep deprived, you get them nice and tired, and then you test how well they drive when they're sleep deprived in a simulator. That would be a within subjects design. And the nicety about a within subjects design is there is no inter-subject. The inter-subject variability does not change, is not a confounding factor. If I'm a crappy driver, which I am, then I'm a crappy driver when I'm sleep deprived, and I'm a crappy driver when I'm not sleep deprived. But if you put me in if you have a between subjects design and you're seeing how well sleep deprived, you put me in the control condition, I'm going to throw off your data. I'm going to be a crappy driver while wide awake. All these sleep deprived people are going to do better job driving than I will. If you do within subjects, I'm crappy no matter what the circumstances, and that comes out in the wash. So within subjects is the same person gets all the different treatments. Between subjects means you have different people do different treatments, and sometimes you need that. So let me see between subjects, why would I want that? Well, within subject, I may not be able, like a vaccine, I may not be able to do a within subjects. I can't give both people both the placebo and the vaccine. If I did, I have an ordering effect, right? I would have to give the placebo first, and they might get and if they get COVID, then you can't test the vaccine afterwards. Oh wait, that's sucky, right? I have to do between. People can also learn; they get better with time, right? And if you have a between subjects design, you don't have to worry about that learning. Within subjects, the first condition is going to have an unfair disadvantage. They're going to be slower, and then they get better, like driving. Or I might get more tired, and so I get worn out over time, and then it's an advantage to be the second condition. So normally you just reverse the order of those conditions for half the subjects as well, and then you test to see if that ordering effect has an effect. But these are all things that you would want to think about, and I would strongly recommend, if you're going to do something like an experiment or some kind of inferential statistic on this project, make sure you talk to me first, just to make sure we line everything up. So my question is, what do companies think of us? We have a co-op program. You guys go out in the world afterwards. What do you think? What do you think people think of us? So if the company has one bad interview, like one of you is a really crappy interviewee, and you go after this company and you talk to them and they go, whoa, the Carleton students stink. Is that representative of all Carleton students, that one person? How about 2 bad interviews? How about 3? How many crappy interviews do you need to know or infer that Carleton students are terrible or are great? And how reliable is it? Am I just accidentally interviewing the crappy Carleton students because all the good ones went somewhere else? We have a bunch of sampling errors in there as well. We have errors in terms of who they've picked through when they're picking through the CVs, or their resumes, depending on what term you want to use. So only some of the people are going to be interviewed, and the people that get interviewed are crappy at the interview. Is that an indication that they just chose the resumes wrong? There could be a sampling error. There could be a choice error on the part of the interviewer. It could just be they all had a bad day. It could be that they did the interviews early in the stages and interviewees got better at the time, or they lowered their bar over time. There's a number of other factors, but even if you remove all those confounding factors, how many people do you actually need is the question, or one of the questions. So this is where the student t-test comes from. Student meaning is a pseudonym for I think he was a chemical engineer / statistician working at Guinness. I always forget his name. I'd have to look it up again. But he did not want his, this is at a particular time. He went essentially on a sabbatical and did not want his bosses over at Guinness to know he was doing all of this statistical work during his year off. So, year off. He was doing a bunch of stats work, so not that much of a year off. And so he devises this idea of a t-test, and he calls it the student t-test because it's his pseudonym. It is the statistical likelihood that the difference in the means between two samples is due to random chance. So the people that get the vaccine get it, 20% of the time. The people that the placebo have a 2% chance of getting COVID-19. The people that have the placebo have a 10% chance of getting COVID-19. What are the chances of that being purely due to random chance? And working under the assumption that you've randomly selected people, and so therefore the chances of them going out to a big super spreader party, their chances of them licking a fire hydrant or whatever the case they're going to do, all of that it sort of comes out in the wash. They're truly randomly selected. So you compare the means of two conditions and you determine if it's due to user sampling, right? Or if it's just, is it random chance? Is it user sampling? Is it, or is it due to some actual factor that you have there? And the big thing is you need to presume there's a normal distribution. If you do not have a normal distribution, you can't do this. You have to do something else, like a chi-square test. So here's the idea. The null hypothesis is that there is no error. We are checking to see if you take a particular mean. So if there's an effect size, you would expect to have some kind of effect like this. If you a null hypothesis, you would expect the distribution like this. Here is the sample that you get. So here is what they actually measured. The experimental condition gets tested and they get this point here. Null hypothesis says they should get it around in this distribution. This is what the control condition gets. Over here is what the alternate hypothesis, if there's an actual effect of the vaccine. And here is one of your samples. A type 1 error is the really bad error, which is saying, what are the chances that there is no difference between the vaccine and the placebo? It just happens that this one person or this group of people, the mean that they got, this group of people have, this response, despite the fact there is no difference between the vaccine and no vaccine. So the vaccine does nothing. This is what the experimental condition gets. What are the chances of that happening? It's this much here, right? This is how off, right, you are. The other way is the type 2 error, which is not remotely as bad, is there is a difference and you conclude, no, there's no difference between the vaccine and the placebo. So you conclude there is no difference, but in fact, there is a difference between these two groups. So this is actually what the data looks like. If theoretically we tested the entire population, here is the people that get the placebo, here are the people that get the experimental condition, and you're concluding there is no difference because you tested a small subsample and you couldn't tell the difference between this group and this group. What are the chances of this happening? It's about this area here. So that's a type 1 and a type 2 error. So we might have things like this, right? I have a general population. Here are the two samples. Here is the normal, this is the placebo group. This is the experimental group. I'm claiming that there are two different things, but it could be I have this one and this one right here, right? It could be that I just randomly happened. What are the chances if I randomly sampled and I got this for the placebo group, this for the experimental group? Or do I actually have an actual effect? That's what a t-test gives me. But other tests are doing very similar things. Here's the thing. So the research hypothesis, normally you would have people are faster at doing this condition than that. Or my system allows me to find errors 20 times faster. Or faster than this other condition, at least. Not 20 times faster, but faster than this other condition. Given that you're saying that there is no difference between the default standard, the old way of doing it, and the new way of doing it, that's the null hypothesis. My system made no difference. Can you conclude statistically that then if the null hypothesis is false, as in there is an effect, whether you notice it or not, there is an effect. There is a difference between the current system and the old system and the new system. I reject the null hypothesis. I say there is a difference between the two. That's the right decision. If I say I do not reject the null hypothesis, it's a type 2 error. I'm saying there is no difference, and in fact there is. So the vaccine doesn't work. We're concluding the vaccine doesn't work. It actually did, but your statistics didn't let you make that conclusion. That's a type 2 error. That's the good kind of error. You don't want them, but it's better than the other kind. A type 2 error means you're playing it safe, but you shouldn't have played it safe, but you're playing it safe. It is not rolling the dice and with your child's tuition at Vegas, right? It's playing it safe, not speeding on the highway, even though you could speed a little bit. Right? It is the safe thing to do, even if you could get away with a bit more. If the null hypothesis is saying there's no difference between the two of them, and in fact you say there's no difference between the two conditions in reality, and you reject the null hypothesis, all right, right decision. Type 1 error is the bad one. This is the one that doesn't get you tenure. This one that gets you kicked out of university. This one what gets you banned as a researcher. This is the absolute no-no. The type 1 error is a thing it should keep you up late at night worrying about. What our p-value does, it tests what the probability of a type 1 error is. If you conclude the vaccine works, or hydroxychloroquine, or whatever the heck Trump is promoting, right? They're saying that is effective, and there's no scientific evidence. It cannot disprove the null hypothesis. If it made no difference in patients and their survivability or their ability to get the disease, if you cannot prove if there is no difference in those two populations when you do the experiment, but yet you conclude that it is a useful drug to give people, that is a type 1 error. Those are the big no-nos. You do not want to say this drug does something and then find out it doesn't. My personal favorite one of those, just because my kid's on the autistic spectrum, but the whole link between supposed link between autism and vaccinations, right? Not true. Well, at least we do not have solid, sound scientific evidence linking autism. It just happens to correlate. You get diagnosed with autism at the time you get your measles, mumps, rubella vaccination. That does not mean the person did not have autism before that. Lots of people have been studying this, but one person concluded, and with a small sample size, that it did cause autism. And we're still trying to fight off that with people saying, "Oh, it does cause autism." No, one guy who got disbarred from the British Medical Institute, one person was able to conclude that it caused autism, and that paper has then been retracted since. When we're talking about t-tests, I don't even think we need the independent means, dependent means. If you're talking about two different, if you're talking about a within versus between subjects design, between subjects design is t-test with independent means. You have two different samples, you have a bunch of different data, and have no information about the comparison of the distribution. You're assuming a random population, you're assuming a normal distribution, and there are two different populations that you're sampling. Not within subjects design, this is between. And by the way, if you want to do this, I would love to see it on your final reports. Throw in a t-test if it makes sense, if you're doing some kind of controlled experiment. Love it. Most of the time we were going to just be usability tests, but something that you can look into. they're easily available for most of you for a lot of things. I think even Python is going to allow you to do that. And essentially, the t-test will give you a p-value, which is the chances of a type 1 error. And that's the critical one to make sure that people can figure out what your math is. If you do not have, by the way, for future reference, if your p-value is over 0.05, you are not allowed to conclude anything. It is a big, hard no-no. You are not allowed to say, it's close to that. It's sort of significant. It would be significant if we had 2 more people. You cannot make any conclusions. People do anyways, but you're not supposed to make any conclusions if it's above 0.05. Okay, and this is how you'd report it, but I don't think we need to go into the details. Most of you are not going to be reporting one of these. We're talking about the degrees of freedom, how many people you have, how many different conditions, and that's part of your t-test. Okay. I don't think I want to go over this, so I'm actually going to remove a lot of this stuff for the actual slides when I pass them off to you guys. The big thing is for when you're evaluating a system, the conclusions you make about you, if you're talking data mining, the conclusions you make about you or the conclusion you make about the population are dependent upon knowing what sample of your population you're getting. If you're actually getting a representative sample, if you are actually figuring out, or if you're getting a subset, and if you're getting a subset, how do you know one way or the other? You can do a lot of these statistical tests without necessarily having a user and doing an actual experiment in front of, doing an actual controlled experiment. You can do it by, analyzing log data. So Netflix recommendations for me. It's like a within subjects design. It's going to have similar things. It is what I watched before, what I watch afterwards. Do I tend to prefer this thing over that thing? Is there a good statistical chance that I'm not going to like a romantic comedy, but I'm going to like an action movie or a sci-fi movie? Yes. If you look at my history, that is how I'm looking at things. You can figure out if people would, people like the Umbrella Academy based off of what they've liked before, what they liked afterwards. In fact, that's when Netflix started, when they made House of Cards. They analyzed what people were watching on Netflix, what they were ordering before they made their first show, and they concluded that they liked political intrigue and they liked Kevin Spacey, at least back in the day, and therefore that's why they made House of Cards with Kevin Spacey. It's based off of looking at representative samples of the population, seeing what their preferences were and what kind of correlations they had. All of this is based off of what the chances of it just being coincidental they kept on ordering Kevin Spacey movies. But the statistical models you make are only as effective as knowing the distributions, and knowing what assumptions you're making about your users. And if you don't know what your assumptions are, if you're just randomly guessing, if you make conclusions about certain things, you may be making the wrong conclusions. If you assume that just taking volunteers for a vaccine gives you a representative sample, you're wrong. And the conclusions you make about the vaccine are going to be wrong as a result. It's a garbage in, garbage out problem. And so therefore, knowing what the distribution is, knowing what the limitations of the data are, is a critical first step in knowing how to analyze things. Okay. So for me, at least, what I want you to do for your projects is know what kind of data you're dealing with and how it's distributed. Choose your classical statistical analysis accordingly, right? What kind of distribution metric you're going to give me, like standard deviation? Are you going to give me the mean, mode, or median? If you're going to do a test for statistical significance, figure out what you need to do. You can look it up. That's fine. This is just one t-test is just one type of statistical test, but ask for advice because there's way too much stats for me to go over. There's entire courses on stats. I would just want to give you a sampling of different parts and how to look at things. When we're talking about inferential statistics, though, you need to know what kind of distribution you have and what kind of test you want to do based on those distributions, what you're trying to prove in the end. And most of the time, it doesn't happen by accident. You need to know if it's between or within subjects as well. Okay, when we come back next time, I'm going to briefly talk about machine learning and data mining and see where we go from that, just enough to see where the human side of things are. All right, thanks everyone.